shaking like a wild tambourine. Skies are canvas painted in electric green. Clouds are dancing like a dream. In the skies, turbulence, it's what we're reaching high. Feel the bump, feel the shake, let it take control. We're spinning through the heavens with a restless soul. Ride the chaos, let the rhythm collide. Turbulence is the beat of this cosmic ride. Seatbelt tight, but my heart's flying free. Through the chaos there's a strange melody. Lightning flashes like a disco strobe light. We're surfing through the storm on a Saturday night. Feel the bump, feel the shake, let it take control. We're spinning through the heavens with a restless soul. Ride the chaos, let the rhythm collide. Turbulence is the beat of this cosmic ride. Up and down like a kaleidoscope spin. A carnival of chaos where the groove begins. The universe whispers in a funky tone. Turbulence is the key to the unknown. Feel the bump, feel the shake, let it take control. We're spinning through the heavens with a restless soul. Ride the chaos, let the rhythm collide. Turbulence is the beat of this cosmic ride. Blast off, rocket zoom, I'm cosmic now, no tether. Stars be dancing wild like they groove into the weather. Ganymede's a player with its subsurface sea, holding secrets deeper than the Milky Way's decree. Got that icy swagger, but it's warm beneath the skin. Oceans flowing quiet where the cosmic dreams begin. Jupiter's my DJ, spinning storms in red and gold. Great red spots of vortex sucking stories never told. Funky ass cosmos, we vibing in the void. Ganymede's the spot where the stars get overjoyed. Galaxies be twirling, supernovas pop and spark. We grooving through the universe, lighting up the dark. Io spitting lava, volcanic rift so hot. Europa's got that chill, icy grooves that never stop. Callisto's in the back, scarred up, keeping it real. Moons of Jove be jamming, cosmic funk's the deal. Ganymede's the leader with its magnetosphere so fly. Auroras paint the sky like a neon lullaby. I'm sliding through the ring, Saturn's got that icy bling. Uranus tilts it sideways, doing that funky thing. Black holes spinning vinyl, warping space and time. Nebulas be painting clouds, cosmic art sublime. I'm dodging asteroids, grooving to the beat. Comets trailing fire, bringing heat to every street. Feel the bump, feel the shake, let it take control. We're spinning through the heavens with the restless soul. Ride the chaos, let the rhythm collide. Turbulence is the beat of this cosmic ride. So let's bounce to the cosmos where the moons and stars align. Ganymede's the king, dropping beats that blow your mind. From quasars to pulsars,
Yeah, that's right. As promised, I'll be talking about quantum physics today. Did I who did I promise that to? I don't know. But if I did make that promise, I would be fulfilling that promise today. If I indeed did tell anyone that I'd be talking about quantum physics today. So that's what we'll be doing. Hope you're excited. Just get that. Let's get that rain purr come in. You know, just a little bit of rain purring into view. It's perfect. It's perfect. Now it is drowning me out a little bit. Now it's perfect. So I decided, last time we did Friday, right? We did a Friday stream last time. Holy guacamole! Who's getting their soda pop? Day Armor. You better enjoy that. If you do not enjoy that, well, then you did not enjoy your soda. Yeah, it's a damn shame. Our topic for today will be quantum physics. I got the. That is There's a quarks. It's a quarks, and what is that? Gluco. Gluco is it keeping them together? Those are quarks. So very small particles. All right, very small. And that's the only recorded photograph we have of them, like in a cluster, because they're way smaller than like what you think. Because like those fuckers make up like a bunch of those would make up like atoms and stuff. They're like, I mean, it's quantum, so it's small. That's a photon. That's what a photon looks like when it is measured. And that, I think it's called the Haricure, or something like that. It's basically a fucking donut magnet, and they have a ball of plasma contained within the center of this device. So it's basically like a miniature sun with like a magnet just holding it in place. Yeah, we're doing a physics stream tonight. Well, not physics actually. We're doing quantum physics. A little different, right? It's more theoretical than anything. I feel like. We've changed the office marginally today. As you can see, it's no longer daytime. It's in fact nighttime. So we don't really get to see outside today. It's a damn shame. The rain's still going pretty bad. You know, we still got a lot of rain. Oh, that guy's still doing his thing. He's swimming through the cosmos. You know, coffee cup still empty. Still empty. Yeah, I don't know where to get coffee. I would love to fill it up with a hot beverage. You, you wanted to audit this course on quantum physics? I bet it's just very fascinating. So we got this side of the room now too. We got more room. We got more room. I decided to make more room. We got this stuff over here, but we got more room over here. And we got hey look. Whoa, what's this? I tried to pick it up with my hands, but that didn't work too well. Alright, well there's a force field there. A quantum force field preventing me from touching that. And we got radio here too. We got radio. You know, we could bring it with us. You know, walk around with it. You know, it's like a boombox basically, but we're gonna keep it squarely in there. We'll keep it in there. So yeah, I looked up quantum physics. Curious. I didn't know too much about it before this, I'll be honest. Yeah, got a nice little. Hey, thanks. I've been working on it. Well, I mean, it looked a lot worse on episode 1 of this segment. Like every time I update it, I try to add some more stuff. I think I'm at my limit though. I don't think there's much more I could add to here, so I guess I gotta start working on, I don't know, different environment. You know, just for shits and giggles, really. I feel like. Where's my paper lunch sack? Well, I do believe it's still where it used to be. I mean, it's starting to smell pretty bad, so, you know, I don't even want to open it. You know, if it smells really bad while it's closed, I can only imagine when I open it, it would smell worse. So, I keep seeing flies going into it and out of it, so I assume they have like some sort of home colony in that bag. So I'm not going to disturb it. I would not dare disturb that. That's life. I mean, if we stick our head through the actual window, we can see the outside. You know, it's not very interesting out there. But yeah, we got quantum physics. Hello, Cake. Hopefully you're ready for some quantum physics today. 'Cause I sure am. Alright, so I got a lot of notes. And I feel like if I read them out of order too badly, I'll get confused. So I'm gonna try to structure them a little bit this time. Get the hell out of here, coffee cup. God. I'm trying to fucking touch my buttons over here and the coffee cup keeps getting in my way. I just don't appreciate it. I don't appreciate what that coffee cup was doing to me. It doesn't even provide me with coffee. Alright, so I'm gonna pull one out of the hat at random, and we'll see. We'll see where this leads us. Well, that one's not that. We gotta talk about quirks before we talk about that one. No, that's not good either. Oh, ooh, that's a good one. We'll put this one on the table. That's a good one. That's a good one. No, that's not the one. Oh, that's a good one too. Oh, that's a good one too. But you know, oh, here we go. Perfect place to start it. Quarks. All right. So a quark is the smallest. It's basically like the smallest Lego block that would ever exist, and they are the smallest point of anything. Any potential object you see, be it a human being or a fox or a fucking fire hydrant, is made up of billions and billions of quarks. And everything is, and they are the smallest quantum object we can actually see. How would quantum physics feel about an aquarium date? So quarks. Let's see what we got here. Yeah, I got it. Oh yeah, there's 6 types of quarks, which confused me for a lot of time. Did you know there's 6 types of quarks, right? There's up, down, top, bottom. There's no left or right. You know, there's no north, south, east, or west, right? It's just up, down, and top and bottom. Those are 4 types of quarks. And the other 2, one is called the charm quark, right? And I'm just like, what the fuck? None of this makes sense. And there's another one called the strange quarks, or quarks, right? Like a strange quark. Now, from what I learned, the charm quark are basically a thing that happens when you basically like what was it? Basically like if like you mash 2 quarks together, the explosion or whatever would be the charm quark, because like it's basically a charm quark is the process of a normal quark just like basically decaying into like a bunch of other different types of quarks. So a charm is like not a charm quark is not like a solid object. It is like a temporary 1/trillionth of a second like reaction that they've sometimes like observed. We also have the strange quark, which are just very rare occurrences in labs where quarks react really weird. And it's rare. Both of those. The charm and the other one are rare. Now, normally quarks, like an up and a down one, or a top and a bottom one, they're basically connected. They connect like Lego bricks, and they have something called gluon, which like, you know, keeps them together. Let's see. Yeah, charm quarks come and go into existence in trillionths of a second, and then they change into other different types of quarks. So they're there for like just such a small amount of time. It's almost irrelevant, but they exist. But that's a basic quark. It's like the smallest fucking. It's the smallest particle you could probably reason, until we find out that quarks are made up of like 10 trillion bazillion other particles. You know, it's all like just micro scale stuff. The quantum stuff is just like the smallest point that we're able to like barely observe, and we do a poor job of it too. So what we got here? We got more. Let me look for this other one. anti-quark, right? So there's quarks, and then we have anti-quarks, right? The opposite, apparently. So an anti-quark seek out a quark, and then they annihilate each other. And there is energy formed from the annihilation process of these things just fucking killing each other, right? Basically, it was discovered that after the Big Bang occurred, an entirely equal amount of quarks and anti-quarks were dispersed into the just everything, right? And these things were literally like the anti-quarks are designed to just annihilate quarks, right? So it's 50%, 50%. But we have like there's no, you can't really observe an anti-quark anywhere, like antimatter basically, stuff like that. You can't observe it. It's like almost a theory, but supposedly those were the two things that came out. As a result, we have a lot of quarks. We have a lot of particles that have built up into planets and galaxies and shit like that. And science is like genuinely confused at why we don't know, we can't find antimatter, because antimatter is like an essential part of the Big Bang like process that happened, that formed planets and formed life and formed everything. Yeah, it's funny. The fucking anti-quark is just like, I don't understand why it exists other than to just annihilate like it's its other form. It's weird. Yeah, but they build up, but basically every planet, every galaxy, everything is built up of these quarks. And it's a damn miracle that there is even anything that exists, because mathematically you would think 50% of each were created, they would have, just 100% chance they all annihilate everything, and the universe as we know it would just be a black void with nothing there. But that's not the case. One thing is that we can detect antimatter. And we detect it in the most fucked up circumstances that we can actually imagine as human beings. We detect antimatter during pulsars and black holes, which pulsars and black holes are essentially like kind of the same thing almost in a way, except one is like just spitting out shit and the other one's sucking in shit, So basically, it's called annihilation events, is where antimatter shows up in a situation where we can actually like scan it and document it. Which I guess the Big Bang is an annihilation event for sure. Oh, let me see what else I got about quarks. Oh, we got dark matter here. Super fluidity. Oh, that's gonna be a good one. Fission and fusion. Oh my god. Quantum computing. Quantum tunneling. Quantum decoherence. I see. Oh, that's gonna be a good one. Superposition. This one took me like fucking an hour to wrap my brain around. The Higgs boson. All right, that's an interesting one. So I learned this today. I had no idea what the hell the Higgs field was, or the Higgs boson, or anything like that. Right? This is about the Higgs boson, but I'm going to tell you what the Higgs field is, unless I got notes about it, which I may not. I may not have wrote down notes about the Higgs field, but I'll tell you about the Higgs field because it's fucking weird. It's really weird, in fact, because let me see. Where's my whiskey? I'm sorry. I need I'm talking about shit that's insane. It's fucked me up when I read about the Higgs field. Okay, so basically everything, the Higgs field is a provable thing. It exists, and it's essentially like an ocean. Like, say our planet, our universe, our galaxy, everything is in an ocean with like a liquid that is so like non-dense we can't even like perceive it. It's unperceivable. But the Higgs boson was a experiment by the Large Hadron Collider, and they smashed, they would smash atoms together in a 12-mile long circular magnet tube, basically, and see what happens. The Higgs boson was the result of one of those impacts essentially creating just a ripple in like the space-time continuum, basically, and an observable ripple, which proved that there is some sort of force. There's some sort of like matter that exists undetectably to us, and that is primarily where quarks and particles and photons and all this weird shit that is almost indecipherable for us to see, they travel along the Higgs field, basically. And the Higgs boson was like 2012, I think, is when we found it, when we discovered that, yeah, in fact, there is some sort of like undetectable liquid. We're all submerged in it, so it's flowing everywhere. And all these weird particles, all this quantum like particle stuff, it exists through that. It uses that as like movement. It's weird, but there is some weird aspect to like the Higgs field. It freaked me out. And it also comes to basically the Higgs field works in a way where as these particles swim through it, they gain weight slowly. Weight actually exists mainly because particles travel through the Higgs field, accumulate, create, creatures or people or anything. It's particles. We're all comprised by it. So essentially, because of this Higgs field, this invisible sea of liquid around us, that is how generally everything accumulates weight and mass and stuff like that. On a quantum scale, I guess. Let's see. I'll read it off. That's what we got. Oh my god. Where am I facing? Okay, I'm facing the wrong way. So basically, it's the Higgs boson. The Higgs field it's subatomic. It's so small, like it's impossible for us to even like understand, especially with our naked eye. Because like atoms and like microscopic stuff is one thing, but like quantum studies go beyond that. They go deeper. They go it's more micro, like oriented. Let's see what else we got here. Oh, EMC2, energy turning into mass, is associated with the Higgs field. That's the EMC squared thing. That is basically Einstein talking about the Higgs field as itself. Let's see. Yep, and quarks only appeared right after the Big Bang, but I think that's unreasonable. Who knows what the fuck was there before the Big Bang? That was like... what, like 100 billion million years ago? I don't consider anything that old to be valid, like, information. No matter how scientific you are. Holy shit. I'm gonna put this down. Get repositioned. Okay, we got more. We got a bunch more. So this one can go over here. We got some weird stuff in here too. We're just trying to ease our way in. Slowly but surely. Because you guys need to understand what a quark is before I can start talking about this other shit, I feel like. It's one step at a time. So we're going to talk about dark matter. I feel like it. I think dark matter is fascinating. Is dark matter quantum physics? I don't know, but it's so super small it may as well be. And like it may as well be. So dark matter isn't visible, and it makes up 25% of our entire universe. The galaxy, whatever, right? Basically, we know it exists because this stuff tugs on gravity. Like, it definably exists. Basically, when we assume that dark matter, like, shapes our universe, because it helps, like, planets and stuff clump up, and since it essentially somehow creates gravity, it shapes, keeps everything kind of like stuck together almost. We just don't know what the fuck it is. Apparently they do. Well, it's like theoretical, but they claim the particle is called the WIMP, which is a weakly interacting massive particle. These particles, the WIMPs, they don't interact with really anything around them aside from gravity. We've never observed dark matter, and we can't trace it or anything. There are some theories. Dark matter is basically what is called a superlight axion, which an axion, I said the quarks are the smallest thing that exists, right? Well, I lied, because an axion is so much smaller than a quark, it doesn't make any sense. A quark in itself doesn't make any sense. So basically, these super small particles, these axions, are like 1/1,000,000th of a size of a quark, which is, a quark is basically the smallest perceivable thing we got. So an axion wouldn't even be, we would never have the technology to detect one of these things. But they basically cluster up, and there's so much goddamned, like, mass built up, because there's, 8 bajillion trillion of these things in the dark matter, that they inherently create gravity, because gravity is conducive to mass, like the mass of an object. So if you have a bunch of these tiny little objects doing their thing, there's a chance that it could, even no matter how small they are, could create gravity. We've never detected it before, though. That's the main thing. Like, we don't know why gravity exists. We don't know what dark matter is. Axiom, WIMPs, all that stuff is just theoretical. None of it's been detected. It's, a lot of this quantum stuff has been, like, observed in labs. It's proven. Dark matter is still a weird mystery that nobody quite can put their hands on, but I assume it's got something to do with this quantum bullshit, It would just make the most sense. That's dark matter. But yeah, it's interesting. But dark matter is interesting. Antimatter, because antimatter is essentially a thing that exists where if it touches matter, it annihilates the matter. So you really don't want to be looking for antimatter, I feel like. I think that would be a very terrible thing to do. That'd be an awful idea. Alright. Large Hadron Collider. I don't know if you guys know about it. Probably do. Well, I'll be right back. I've just lost one of my windows. Hey, there we go. Oh, lost this one too. Well, I'll just get it back. Hey, perfect. Yeah, you gotta be careful where you step, You never know. You never know when you're gonna push the wrong button on your arm, Fuck up all your screens. It happens. Streaming in VR. It's got its loops, it's got its hoops to jump through. So, Large Hadron Collider. I'm sure some of you know about it. I would hope so. I mean, if you don't, that's fine too. Why would you need to know about the Large Hadron Collider, right? Well, it's a 17-mile long underground structure. It's shaped like a ring, like a donut. Basically a big ring. It smashes protons together because it's basically a long magnetic tube, and the protons go through it. And they go through this 17-mile long route, and then they smash together at the end. It's very fast, like speeds that they smash them as well. The Large Hadron Collider was the reason that we figured out that the Higgs boson existed, so we could prove the Higgs field is a thing, that these particles indeed are basically swimming through like a liquid of some sort. We've actually discovered new entire particles using the Large Hadron Collider too. One's called the baryon, which is basically it's like a super heavy particle with like charm quark qualities to it, which means it probably explodes. Basically, that's what a charm quark is. It's the explosive decay of a like a quark, basically. The Large Hadron Collider also led to the discovery of anti-hydrogen, which is a form of antimatter, essentially. Because at the Large Hadron, the Large Hadron Collider has been the people there have been attempting to create antimatter. They want to create antimatter so they can observe and study antimatter. And so, I mean, we have gotten close because we've literally made anti-hydrogen, right? So we're getting close to making particles that have like anti-properties to them. Because then they want to trap, they basically want to trap antimatter in like a magnet cage. And so far we have not succeeded at this. Luckily, I feel like that's like an awful idea. Because they say they want to do it to figure out why the universe lacks antimatter, but I'm like, well, maybe we shouldn't. Maybe it doesn't matter. It does sound dangerous, doesn't it? Because as far as I know about antimatter, it exists to annihilate matter, and it's like that's a very specific word to be using for destruction. You know, annihilate. It's like holy shit. So yeah, luckily, I mean, well, the Large Hadron Collider did. I mean, the people do claim that the Large Hadron Collider is the reason that, like, the Mandela effect exists, because we, like, fucked up the timeline with it. So people kind of, like, assume, like, oh, anything beyond, like, anything before 2012 got changed, you know, because that's when they did the Large Hadron Collider did that big test that actually showed us the ripples in space-time, to make us realize, okay, there is some validity to like quantum stuff. Like it's not like magic, it's an actual factor of life. It's weird. It is. There's a lot of validity to it, and I think that's cool. That's nice, but I don't like. I wish it were all fake shit, right? Because God, then I could just like be like, I don't care. I don't need to look into that. But no, if it's an actual thing, you gotta keep in mind like the facts of it, you know. If quantum shit is real, I don't know. Like there's a lot of like different theories about how quantum mechanics work. The shit, you might be able to exploit the universe, you know, if you use it right. You know? Well, we'll get into it, but there's like quantum entanglement and superpositioning and stuff like that. Really weird concepts that sound really stupid until you think about it and go, that's kind of weird actually. You know? But we've talked about quarks. I looked at my paper, my notes. That's all I have about quarks. So I'm going to point at quarks with my emphasis stick. With my emphasis stick. Boop, 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 boop. So, quarks. That all these little circles, the little circle parts, those are all quarks. They could be up quarks, they could be down quarks, they could be top quarks, bottom quarks, but they're not charm quarks, because charm quarks like explode, and all that shit around it is the gluon. So a bunch of these fuckers will combine together and make, you know, like the small stuff, like atoms. You know, an atom is just a bunch of these things, basically. Because that's how small it gets. That's like the smallest we can conceive life. And it's I mean, it looks like what you would expect, I suppose. A bunch of damn balls, really. You know? But, you know, that's the quark. Do I believe in them? No, but science has proven that they're probably a thing, so there's no believing or not. You know, it's Ripley's Believe It or Not with those. You believe it or not, because it doesn't matter if you believe it or not, you know. So, we're going to bring up the theory of... What do we got here? This is called quantum entanglement, otherwise known as spooky action at a distance, which I'm sure some people have had to hear that one, right? That's an Albert Einstein like one. Oh shit. Yeah, spooky action at a distance. Basically, it has absolutely been proven. Oh. Jeez Louise. It's been proven that like two particles can become quantumly entangled, which means they will perfectly copy each other in terms of their movements, their distances, their spins, their rotations. They're basically everything they do is quantumly entangled to something that could be 8 bajillion miles away or 5 feet away. But whatever it is, once an item is quantumly entangled, it remains that way. There's no stopping it. And this has been proven. It's been proven to such an extent where we can replicate it in like laboratories commonly as just a common practice. It's completely like proven. There were some tests called like the Bell tests, where they measured the states of entangled particles, and it was observable, and the test was like a success. The Bell tests were complete success in terms of like, let's figure out if this is a real thing, and it is. Essentially, once an object is entangled, their properties are just permanently linked. So if it spins, the other one will spin. If the other one moves left, the other one will move left, and it's just how it is. I don't know why it works that way, but it does. Now, we can replicate this. We can replicate quantum entanglement in a lab by, basically, we would have to take a quark, a particle, right? And, well, it sounds stupid, it sounds crazy, but it's a real thing. We shoot it through a beta barium borate crystal, right? We basically send this particle through this crystal, and you know what it does? It fucking duplicates it. It creates two particles. Once it passes through this specific crystal, it creates two particles, like a copy of the one we sent through. And these things are like verifiably quantumly linked to one another. Every time they push it through this crystal, it creates a copy that is quantumly linked to it, and it's a real thing. It's not hyperbole or anything. That is just a reliable lab technique at this point. Like we've gotten to a point where we're starting to reliably understand quantum mechanics, and we're utilizing it. Yeah, quantum entanglement. It's weird, but it's actually verified. It's a verifiable thing that kind of blows my mind a little bit, honestly. All right, so with that one, with quantum entanglement, we'll talk about the other side of this coin of weirdness when it comes to quantum positioning, because we have something called superposition. Now, invariably, particles exist in a multi-state, as if they were like vibrating between forms until they're actually like observed with the eyes. Meaning that like particles that you have not observed or tested or measured are in a superposition. That superposition means that they could be doing anything at any time, and it's completely variable. Now these are electrons, like the electron particles, energy carrying particles. Basically things that just form like energy, electricity, shit like that. Now, until you observe them, they are wildly, like, they could be anything. They could be anywhere. But once they're observed, they're immediately, like, sealed into place. Like, their fate is sealed. The moment they're measured or observed with the eyes or anything like that. That particle becomes a, actual particle. It's not some hazy vibration, like it's just like, like an indecisive like particle trying to figure out what it is. Once observed, like the results are like solidified permanently. They did a experiment called the double slit experiment. I'm sure if you probably heard about it. It's pretty popular, I guess. Now, basically, what this showed is that, because basically with the double slit experiment, they'd have two slits, and they'd just start shooting electrons in it and see what would happen, how the electrons pass through the slits, right? So they would have two different things to determine that superposition exists as a thing. Because if they were to measure the beginning process of this, like the beginning process, and they observe the beginning process of actually shooting the electrons through, the results are always going to be one way. Meanwhile, if they don't observe the beginning part, and they only observe like the results of where the electrons headed, it would always be a completely opposite way, which would indicate that by observing these particles, it changed them. Because when they would have like something on the end that would mark like the exit point of all these particles being shot through, so they could measure it like all the way through and it would be one result. But if they just ignored measuring that part and just looked at the the end point, it'd be completely bizarre. Like it wouldn't make any sense. Which means that the human eye, like the human consciousness, has some sort of weird verifiable effect on particles for some reason. There is a legit argument to be had that merely placing your eyes upon something can influence it and change it. And when your eyes are not on something, it Schrodinger's cat kind of principles, until you actually see it with your own eyes, it could be anything. But with the double slit experiment, they actually proved that that's like not just like weird, just human bullshit. No, that's some weird. The quantum physics does work in a really weird way that we are unwilling to accept. So superposition was weird, because for me with superposition, my problem was that I'm sitting here I assume you have to observe it at all points to determine that the particles are acting weird. But it makes sense though that one, you just observe the process completely and you get like all these same results. But the moment you observe, you stop observing it and you only take into account like the last portion of it, it's different. It should all be concise no matter whether or not you're looking at the experiment or not. But for some reason, superposition is like the most. It makes so little sense to me, but it's a verifiable thing that we've like worked out in labs before. To such an extent that we use superpositioning as a like that's what quantum computing is. Quantum computing is basically us using superpositioning and quantum entanglement for all the computer functions. So like we've learned how to replicate superposition. We've learned how to replicate quantum entanglement, both of them. So like it would be silly to say that quantum physics is just theories and stuff like that. There's actually like real, it's minor stuff. It's nothing like crazy major. Two particles sharing the same like sort of behaviors. It's very minuscule if you think about it. Quantum entanglement is not that crazy because it's on a particle level. It's on a quantum particle level. It's not like there's an entire planet that's like linked to another planet. The quantum entanglement does not work that way, because it's all particles. Particles are linked, not entire like masses of particles. So if you think about it, it is kind of a minor factor overall. Like it's not going to do us any different on a day-to-day basis, but it is probably actually verifiably true that quantum entanglement does work. It is a thing. Like we've replicated it in like labs, All right, so we talked about quantum computing, so I guess we'll move on to that one too. Oh, let me breathe for a second. Jeez, I've been talking so fast, I haven't even taken a breath. Gosh. Oh, it's a good topic though. God, I was researching this stuff all day today, and I was loving it, because I learned a lot. I didn't know a lot about quantum physics. I feel like I knew about string theory and like other dumb shit, but I never looked at it. I never looked into it to the degree that like it's actually like kind of a viable thing. I never realized that there's like more meat to this than I thought. I thought I was gonna have a goofy time laughing about like alternate dimensions and stuff, but no, there's real science here. It's really cool. But we still got like 1,000 notes left to go. Sadly, we're not even halfway there yet. I'm sorry to say. So what I'm going to do is talk about quantum computing, right? So quantum computing. Oh. So a quantum computer, basically, uses superpositioning and quantum entanglement and other aspects of quantum mechanics to function. Oh. Oh. I'm sorry. That whiskey just went down a little, went a little rough. Almost fucking burped. I'm not gonna burp on you guys unless you want me to. I mean, I'll burp on you if you want me to, but I don't want to. I would not. That's not who I am. I'm not a burper. So a supercomputer is comprised of like 1 billion fucking qubits. That's what they're called. A qubit is just a little device, it's kind of like RAM or something like that. It's like just a little fucking piece of a computer. But they are what powers a quantum computer. Now they're capable of essentially following the rules of quantum mechanics, and they can use superpositioning and quantum entanglement to like interact with one another. Now the qubits, they have to be super cooled to like negative 400 degrees Fahrenheit, basically at absolute zero, or they will not function at all. That's why the quantum computers are so weird, because you actually have to freeze them. Because we have a few more notes on here about quantum stuff. It all revolves around like absolute zero. Coldness is what's like really like activates quantum mechanics as like a whole. Now, since they need to be cold, they are extremely delicate. Basically, if you're qubits. Now, basically, if you take one of these, like in a quantum computer, they have the qubit, right? Now, they're so delicate that any slight vibration, any amount of heat, any amount of light, any photons that might pass through, anything, any aspect of the real world touching this quantum, that whatever's inside of the qubit, which is a small quantum pocket, if anything from the real world disturbs the quantum pocket, that qubit is just permanently broken. If it gets too hot, anything. Because the quantum, we have one over here about it. It's weird. It's fucking weird. Anyways, let's see. Oh yeah. The point of a qubit, the point of quantum computing, is that like in a normal computer, they use like binary, right? 0 1 0 1 1 1 1 0 1. A qubit is a device capable of both being able to do 0 and 1 at all times, right? That is what one qubit does. It is the simplest process of binary 0 1. However, this is binary with the added thing that it has quantum entanglement on it, and as well as superpositioning, which means superpositioning means that this qubit is constantly in a state of 1 and 0 at the same time. It blurs, it vibrates between both of them. It's never like permanently like a thing, right? It is always variable. And the The quantum entanglement means that every singular one of these qubits, all 1 million of them, or whatever they put in a quantum computer, they're entangled with each other. So it's like instant data transfer between them because they're entangled. Like literally, it's all quantum like pockets, which is weird. However, we're not smart enough to actually make a really good quantum computer yet. These are basically baby computers. They're not that great. They're good at like certain things, but as a whole, you have to put them in negative 400 degrees Fahrenheit cold weather, or it'll break. It'll break so quickly. Hey, Forenzi, what's up? Do you enjoy quantum physics, Forenzi? Because that's what we're talking about today. We're talking about quantum computers, though. Do you own yourself a quantum computer, Forenzi? But yeah, unfortunately, quantum computers are so like fragile and shitty and useless. You couldn't even play like a video game on them. I doubt it. You do? Oh shit! I knew very little about quantum physics until today, when I was like, hey, you know what? Maybe I'll just research this. I'll look into it, and I was like, oh shit! Why did I look into this? Now my brain hurts. Oh, my brain hurts so bad. After that. But it's great. I'm learning so much. It's so cool. I think the biggest surprise is that I found out that like there's validity to it. Like the quantum stuff is not just theories. We've scientifically we use this stuff in labs and stuff. It's a real like science. It cannot run Sekiro. I wish. Are you guys fans of Sekiro? Do we got some Sekiro fans out there? Just watched the Wreck and Sylvarian. They basically, I feel like they went through like an existential crisis while trying to beat Sekiro, and it made me laugh. You know. Hey, and thanks for the follow, Forenzi. It's good to see you. Hopefully you've been doing well, Forenzi. Holy guacamole. Life's weird, huh? Whoa. Hey, don't mind me. I'm just opening my container of water. I mean, it's okay. It's water. You know, it tastes okay. I always wonder about the quantum effects on my water. Can they make me some quantum water? I think that'd be delicious. You know, some water that doesn't exist. You know, in the bottle, it'd be in its quantum state, and then when I open it, it turns into like juice or something. I don't know. It turns out of its quantum state. Unfortunately, we still have like 10,000 notes over here. We're never done. We're stuck in this. I picked a good topic today that had about 10 billion things for me to potentially talk about in. Not like last week, where I just talked about Friday. You know? I went from talking about Friday to talking about goddamn quantum physics, you know? Alright, let's see here. Oh, here's an interesting one. Here's an interesting one. I don't know if this is due to the quantum physics or not, but I found it very fascinating to think about, is that energy, it cannot be destroyed. Energy is like immortal. Well, like energy, it always exists, but it does change forms. But it's never lost. It's never destroyed. It just spreads and moves on, like constantly. And even a black hole cannot destroy energy. A black hole does not destroy energy. It just absorbs it and stores it, and then usually, you know, a pulsar will happen and it fucking spits it back out. The sun's energy hits our Earth. You know, our plants take that energy through photosynthesis. Animals eat that plants, and then other animals eat those animals. And, you know, and then they poop, and then more plants take that energy. Energy is just like a constant thing. It's like genuinely like life force. Like a mana, you know, stuff like that. Even like our tides come from like gravitational energy and stuff like that. Like energy is just a weird thing that we act like it's super finite, but it's everywhere. Like energy is like genuinely like a thing that we could pull from anywhere. And if you look at this quantum shit, it turns out like energy might not be we don't just need fossil fuels and oil for energy. Like that's silly. Whoever Whoever tricked us all into thinking that oil is the only way to have energy is a genius, really. Oh, yes, this ancient dead body muck. We gotta use that to power our cars. Yeah, these dead dinosaurs that turned into black muck. It's stupid. It's a worst. Fossil fuels are like the worst idea that we could have thought of for fuel. Doesn't it freak you guys out to think that all of our power in this world right now comes from literally just like ancient dead animals and trees and all that stuff? Like that's what we use for our energy source. It's just we burn corpses. That's what oil is. It's stupid. It's the worst. Does that have anything to do with quantum physics? That energy can never be destroyed? No, not really. Not really. Not really. Holy guacamole! What was that? Oh shit! I gotta look now. Holy guacamole! Armor. Hey, thanks for that subscription. You know, if we were all luckier people, I would have been playing Silent Hill 1. When you did that, and you'd see my little screen. But I don't think I have it on here. I don't know. Maybe I do. It's the only thing I don't like about the VR streams is that my little. I don't know. I have like these little video screens that show all my redeems and stuff. I just don't have them on here. I appreciate that. What the heck? I appreciate that. You know, it's probably because I told you about how energy can never be destroyed, and it inspired you. You're like, holy shit! You know what? That's really cool. What the? Well, so it gave me some energy. Yeah, I know. I'm just saying, you know, it's this weird shit. This is my. Granted, I've never studied quantum physics. I'm no expert in quantum physics. I did a lot of research today and was very happy with what I saw, and that's about my knowledge of it. So, anything you take away from here, I mean, it's at least verifiable information, but as far as my understanding of quantum physics, I don't know. I have no idea. It's honestly, it's kind of broke my brain a little bit today, just looking into it. I thought I was going to have a laugh and a hoot and a holler. I had none of those things. I felt like existential dread, mostly. So, I mean, I don't know if nuclear energy really ties into quantum physics that much, but I think so. So fission. Fission is essentially the result of splitting an atom in half, right? And when you split an atom in half, it explodes, right? You guys have seen an atomic bomb. You understand what a fucking splitting an atom does. Now, basically, an atom is one of the smallest things, kind of. Quarks are smaller, and apparently axioms, which may be what dark matter is, axioms are way smaller than quarks. So, an atom may not be the smallest thing ever. So, basically, with fission, they don't just split one atom at a time; they split a bunch of atoms at a time, and those create series of explosions that create energy. And in the event of like the case of a nuclear bomb, they have to split like 1 million atoms at once to cause the nuclear explosion. It is not a simple process, actually. You would think a nuclear bomb is just, you just load it up with, some fucking God, what is that shit called? I don't know, just some radioactive shit, and you just shoot it, right? No, you have to actually like split like 1 million atoms at the same time to cause a chain reaction that causes like a nuclear explosion. Who thought of that? Who was the genius who was just like, all right, I perfected a way to like trigger 1 million atoms splitting in half at the same time for this bomb. Like, no wonder it's so tough for people to fucking make nukes. Good God. I didn't know. I thought it was just like, I thought it was simpler than that, but it turns out it's like, it's actually like kind of bonkers. Like the real science you have to do. That being said, even if it is a million atoms is still what, like smaller than this fucking part of my hand, right? Right? Like, how does that cause a nuclear explosion anyways? It doesn't matter if there's a million of them, right? I have not seen Oppenheimer. Is that a good movie? I kind of want to, because I mean, I'm not like one of those war whores who like just loves war and shit like that, but I do like science, and like I'm not really obsessed with like World War II, I guess. You know? Okay, yeah, because I don't like movies that glorify war. I don't like war. I'll tell you what, like, if there's anything in this world I don't like, it's war. I think war is awful. I think war sets us back every time. I think war destroys beautiful ruins. I think wars get rid of like cultures. I think that in our past, a lot of like probably more peaceful civilizations and cultures have probably been completely wiped off the map, and their books destroyed because war just benefits the savages, really. More about the person. I might watch that. I think I might watch Oppenheimer. That might be good. Because I have a feeling it's good. I know some people are like, oh, it's boring, but like, I don't know. I'm the kind of guy who doesn't really like explosions and loud things on my screen. I like, kind of like a chill movie, you know? Like, I watched Blade Runner the other day, and I was just like, wow, this is great. Like, it was just like 2 hours and 30 minutes of kind of just like, almost like cyberpunk ASMR. It was great. Really good. Now, I talked about fission, and fission is the brutal splitting of atoms in half, right? We also have fusion. Now, fusion is weird. Fusion is so weird. Oh, I thought nuclear fusion was like the same thing as nuclear fission. No, nuclear fusion is something we can't even figure out how to do yet. Now, let me see here. Let me check my notes. So, fusion is a result of atomic nuclei, like hydrogen, being smashed together to form a heavier atom. So, basically, it's a fusion of two atoms to make a heavy atom. The process that fuses them just like creates a shit ton of energy, basically. And it generates far more energy than any nuclear fission can create. Well, basically, nuclear fusion, if you wanted like an example of it being used, the stars. Every singular star uses a very potent form of nuclear fusion just to operate. Just that's how they work. Now, there's something called a tokamak. A tokamak? Tokamak? Yeah, that's it. I'll show you the tokamak because I found them very interesting. I actually put one right here. Here we go. This is a tokamak right here. Okay. Now it's a half of it. They cut it in half, right? And you see it's like a donut-shaped thing right here, right? And those are magnets. That donut part is the magnet. And what they have here in the center would be a ball of plasma. Like a fucking actual, like, miniature sun that they keep imprisoned within the tokamak. Right in the center here. And the magnet would keep it just stuck here. And that's how they try to harness nuclear fusion. Is by keeping this ball of, like million-degree plasma contained within the tokamak. Does it work? Well, it works for one reason, and that is because of quantum tunneling, which we haven't talked about yet, but we're getting there. We've shown the tokamak, so quantum tunneling will be, honestly, next. So, nuclear fusion and fission, not really a quantum topic, but I think it led to the tokamak pretty interestingly, because fusion has something to do with that. Get out of here. Get on my table. Okay, not you. That. Well, we do have something about quantum tunneling here, but we'll wait. Let me see what else we got. Casimir effect. Quantum decoherence. All right. Nobody freak out. We've only got 5 cards left, which means I've been breezing through this, I think, unless it's like 5 hours in and I just don't realize it. Okay. We're an hour in, and we've gotten through 15 of 20 notes. So, I can slow down. I'm going to slow down. I'm going to slow down, let it all settle in. You know, everyone can digest the information they've been given. Oh. So, since we're gonna, yeah, we'll take a break. This is our lunch break. We've been talking for an hour. I've been talking for an hour about quantum physics. You know, gotta rest my voice a little bit, rest my brain. Well, not my brain. I have a good idea of. It's. We're gonna go back here to the radio. Let's listen to the music. There you go. It's pretty good. Just sit here and listen to some music. You know. So what I've learned about quantum physics is that it's a science. It's a real thing. It's not like hyperbole or anything. And because it's like a real thing, it's a real factor, like a real thing we can actually like replicate in a lab and test, means that, oh shit. Means that it's also pretty lame. Like it's like, there's not a lot to it. In terms of like, there's no fantastic nature to it. It's all rules, it's all vague rules, but it all makes sense. And I don't know. There's also the theory that there's like multi-worlds or like every time you make a decision, it creates another universe, which is retarded. Like, it's just dumb. Like that's the stupidest thing, I think. Like, you're telling me every time I choose to eat like a bologna sandwich as opposed to a chicken sandwich, a new entire universe is created? Well, then that means that there's like, for just Earth, every year we create like, what? 2 million extra universes, right? Because everyone makes a decision like every day, many times a day. So I don't know about this multiple dimension, the multiple world stuff. I think, if I'm thinking about it, I think the quantum spectrum exists as a series of variables all ready to handle any particular situation thrown at them. But just because like that they're ready for multiple variables does not mean that if you make a decision it creates like 6 other worlds. It just, I don't know. I think I think the main upside to quantum stuff would be like the ability to try and predict the future. I think if you wanted to use like quantum physics as like some esoteric thing, you would have to like use it to look into the future and try to pre-plan and plan stuff based on like the quantum, I don't know, just like the quantum like variables, because that's all it is. I don't think there's other dimensions out there. I don't think so. I would hope not. Wouldn't it be very deflating if you realize there's 8 bazillion trillion other universes out there? You know, like that'd be dumb. Like, nobody would enjoy that. Hey, just remember, I got my ad in here so I could throw it. You know, I like to throw stuff. That's my favorite thing. Okay, we've stepped into the back room, the break room. I feel pretty calmed down. I think we can go back and talk about more quantum physics. We've still got 4 notes. We still got 4 more. Whoa. Let's see. We're going to talk about quantum tunneling, because it doesn't make any sense to me, and it probably still won't after I explain it. Okay, so I've tried to write these notes to myself in a way that I can try to at least figure it out. So, quantum tunneling, right? Electron particles have the random ability to pass straight through things they shouldn't. Things that they should not be able to pass through. It's tied to fusion energy, which is the energy the sun uses, more or less. Fusion is 2 atoms being smashed together to be fused into one, basically. You know, we've talked about fusion. You know. So, if you want to think about tunneling, all right, the best way that I conceive to think about tunneling is think about 2 magnets, 2 good magnets. And you know how, like, you try to push them together and it's just like that force in between where you just can't, no matter how much, you know, you can't do it. Especially with a strong magnet, there's just no way to get the opposite ends to touch. What quantum tunneling is the ability to get energy to pass through that particular magnetic barrier that you just normally, it's just an impassable force. And quantum tunneling is essentially particles being able to pass through this weird, you know, like an impassable force, which would be, you know, that magnetic resistance. And so that's all, like, what quantum tunneling is all about, is the fact that some particles can just ignore the properties of anything and just go right through it. It doesn't matter. It essentially allows for electron particles to ignore the magnetic repulsion. And usually it's described as it can pass through a barrier that just simply it shouldn't be able to cross. That's what quantum tunneling is. Now, the main factor of it, that fucking thing right there, the Tomorark. Let me see. They got it written down. The tokamak, that thing right there. The tokamak is entirely a scientific object that uses quantum tunneling, and it works. And that thing probably proves that quantum tunneling is an actual factor of reality. So what it does is it keeps its plasma in the center, and it has a strong magnetic field around it, just containing the plasma energy. But because of quantum tunneling, there's random variable and chances that particles and energy from this plasma can seep out, despite the fact that there is so much tremendous force holding it together. Quantum tunneling allows the energy to escape from it regardless, and we can utilize that energy. And that's like the main appeal of quantum tunneling, is that we can use all this force to keep something contained in a ball, but we can still get energy out of it, no matter how much, like, extreme force we're using to keep it, like, contained, more or less. It's weird. Like, for me, I don't think I'm smart enough to, like, understand all the ups and downs to quantum tunneling. And I'll never be that smart either. I'll never be that smart. You know, it's just a dumb, you know, it's a thing I can never handle. Oh, you know, that's it. That's all I can say. Now, quantum decoherence. Essentially, when quantum particles are observed in a lab, in a perfect environment, they're essentially magic. Like, a quantum object, as a quantum object, is magic. Like, it doesn't make any sense, and it doesn't adhere to any rules of, like, logic, basically. Now, basically, as soon as that particle interacts with the real world in any way, be it a vibration, light, photon, anything, the moment the quantum object acknowledges the real world around it exists, it no longer becomes, it's no longer a quantum object anymore. It's that fleeting. It's like that fragile. The moment it touches anything from, like, our reality, it changes function into a just a static, just normal particle. Now, superconductors, which are very cold conductors, basically, which are, below freezing, make use of quantum decoherence, because if you get something below freezing, like to that point where it's like at absolute zero, quantum decoherence stops happening. When it's frozen to that state, for some reason, like the quantum period of a quantum object can be retained and like kept as long as it's like that cold. So coldness has some sort of weird effect on quantum particles, and I don't know why. Like, what could I tell you? Yeah. So quantum decoherence is essentially when a quantum object is created, I guess, or spawned into existence, it's there very temporarily. And as soon as a quantum object interacts with the air, or a slight vibration, or a photon, or light, or anything that's from our world, it immediately like solidifies into a particle, and it stays that way. There's a quantum period of stuff. It's like the small quantum period where these particles can essentially just do anything. It's like insane when you think about it. Oh, but that's just it. And I don't think anyone has any real good answers to how quantum stuff works just yet. But within like the past 10 years, we've made plenty of breakthroughs about it. So there might be something more to it than we're thinking. I don't think it's alternate dimensions. I don't think it's anything weird like that. But it is fascinating, I think, to figure out like the little gears of our life, how everything works, what pieces us together. We're all made of quarks, aren't we? We're all just full of like weird little tiny, like all our entire body. It's just like 8 billion trillion tiny like little things like formed together, basically. Yeah, so look how many notes we got already done. That's the done list. And that's the not done list. There's only 3 left. As you can see. I need more water. I'm gonna imbibe this water with my mouth. Yep. I can't stop it. On the topic of cold things, we're gonna talk about superfluidity, because it's weird. It's a little weird. Okay, so superfluidity is specifically when we take helium-4, which is a liquid, and I'm sure you know what helium is, like normal helium, right? But basically, we take helium-4 and we cool it to negative 450 degrees, around that point, which is a smidge above absolute zero. This is basically where all thermal motion theoretically stops. Around that, it's a smidge around absolute zero. And this point of like coldness is where almost all quantum shit like starts happening. It's dependent on super cold. It's weird. So superfluid can move through spaces without losing any energy, right? No loss of energy at all. There's no friction, there's no stopping, and its fluidity retains its energy. And it's usually used, like superfluid is usually used in like gyroscopes, stuff like that. Invariably, this is the closest we can get to perpetual motion. As long as this liquid remains cold, it never stops moving, ever. Like it will infinitely, like this liquid will infinitely move for an eternity, as long as it's cold enough, right? Until the temperature changes. Now, the state of fluid, literally, can make it capable of slipping through microscopic cracks, basically. So, in a superfluid state, this liquid can move through, like, much smaller, like cracks than normal. Microscopic ones, in fact. So, now, it's a quantum... The quantum effect of this, of making it that cold, essentially makes the liquid act as a singular wave, as a singular mass of liquid rather than a bunch of particles that form the liquid, right? Like, because it's cold, like it literally like transforms the actual behavior of this helium-4. Yeah, and I mean, for me, I assume at this point, like the fluid is so light, it's almost like non-existent, and it reminds me of the Higgs field we talked about earlier, to where the Higgs field is essentially like a super, it's like a liquid. I mean, shit, it's probably around us right now. You're probably swimming in it right now. Wherever the Higgs field is, it exists around everything. It's in space, it's on planets, it's everywhere. There is some sort of like substance, some membrane that keeps everything around us moving. Like, and it doesn't make sense. It doesn't make sense. Now, also the superfluid, like superfluidity in general. If you get a superfluid going and you have it cold enough, it basically is the best conductor you could ever have. It will conduct electricity perfectly. There's no like loss of anything. The only downside is that it has to be very cold. But if we could figure out how to keep it cold and it not be a problem, like we wouldn't need like wires and shit like that. Superfluid would work. And you wonder, like, for like UFOs and shit like that, they probably use stuff like superfluid and shit like that and quantum this and that. But superfluid's interesting. It's just, you need negative 450 degree, like, at a constant, or this machine will break, or the superfluid will fuck up. So that's the main like downside with quantum stuff, is that you need a specific very cold temperature, and if it goes a degree above or below that, everything stops working. Now, did you know that we have a thing called the olfactory enzyme? Did you know there's a thing called quantum biology, which has to do with the bodies of like creatures and how quantum mechanics does affect us too? Now, olfactory enzymes help your nose detect smells, and they are thought to use quantum tunneling. And your nose essentially senses quantum vibrations of molecules. It's how you smell, and how smells apparently get into your senses. You're smelling molecular vibrations. It's not a smell, which, if you think about it, why would it be a smell? That is just generally how it would work, right? Like, is a smell like a thing? No, but are vibrations a thing you can smell? Well, good. That's how the olfactory enzyme works in your nose. It senses specific vibrations, and then those vibrations tell you, like, well, it smells like this. And then it sends that to your brain. You're not actually smelling anything. You're not inhaling anything. You're basically breathing in. Your nose is detecting vibrations and then giving you a smell based on that. Photosynthesis is another example of quantum biology, to where plants soak up the sun. The sun pierces right through them. From quantum tunneling. and then they absorb it. There's also amylase, which is your spit enzyme, your saliva. And basically, they use quantum tunneling to allow sugar molecules to bypass known barriers in order to be absorbed, which might be why sugar is so bad for us, because specifically our mouth enzymes use quantum tunneling on sugar to just make it bypass all the safety precautions we have, just go right into you. It probably works that way for caffeine and like nicotine too, I assume, right? If quantum tunneling is a thing, would not nicotine and caffeine also be something that quantumly tunnels into you and bypasses all your defensive measures, right? But I don't know. I'm not a quantum physicist. I don't know. I learned about this stuff today. I just did a little research today, and there you go. There's also mitochondria, the powerhouse of the cells. They turn food into energy, and they are theoretically a quantum coherence aspect because they are freakishly effective in terms of how it takes and spreads energy throughout your body. Like, mitochondria are so effective and accurate that it baffles scientists, and they assume that these cells use quantum coherence to basically properly distribute your energy throughout your body with like pure accuracy, because the mitochondria work really well. And then all they do is you eat something, and then the mitochondria is like, hey, we'll just rip this thing apart and spread it throughout your body. That's what eating. Yeah, there's a game called Parasite Eve, which I actually intend to stream. Parasite Eve 1 and 2. So I'm excited to bring up mitochondria a little bit. But yeah, that's what it's for. Mitochondria is essentially what gives all... If you didn't have mitochondria, your body would just die. Because that is the main thing that basically feeds all of your cells. It's so super efficient at doing that too, that it baffles people. That's why mitochondria was brought up in that game, I bet, too, because it's an anomaly. It's a scientific anomaly in our body. Like, mitochondria are bizarre, but they might be a quantum cell. They might actually, like, quantum stuff might not be just some side thing in our lives. Quantum mechanics might actually be just a normal part of everything, and it would probably be beneficial for us to accept that. Like, we need to just maybe accept it, right? Because if that's in our bodies, and our bodies are using like several quantum mechanics in them, who are we to disagree? Oh, got the Casimir effect here. Which is also the last note I have. So anything past the Casimir effect will just be theories, observations, stuff like that. So the Casimir effect is weird, right? So let's say you take two metal plates and put them in a vacuum, like two metal bars or whatever. Two objects. Doesn't even need to be metal. And you place them right next to each other in like a vacuum where nothing can disturb it, right? Now the Casimir effect assumes that they wouldn't do anything, right? Nothing would happen. They're in a vacuum. There's no outside interference, there's no wind, there's nothing. Unfortunately, if you put two metal plates, or any plates, I guess, metal is just a normal example used in the experiments of the Casimir effect, and you put them right next to each other in this vacuum, they will very slowly and surely push together. It always happens. It's a confirmed weird effect where two objects will invariably push together, even in a vacuum, even with no outside interference of wind or anything else. The Casimir effect is what details that. Yeah. Right? Now, what's happening with the Casimir effect is that at all times, even in a vacuum, even in the depths of space, no matter where you are, there are billions of fucking goddamned particles constantly just shooting around just like crazy everywhere, constantly. It is a constant thing. Whoa! Even in a vacuum. So what happens to these two metal bars in the Casimir effect is that, like, between them there's a very small space, right? Because they're next to each other. But on the outside there is like what? Like a whole ass space where all this shit can keep hitting it. So invariably, because there's so much more space outside of the two bars and all these particles are just slamming into it from the outside, and there's less space between them, they're not separating, they're being pushed in slowly. And the Casimir effect has been proven to where that just happens. That happens to everything. Now this is where the term 0 point energy comes from. The fact that no matter what, even in a vacuum, energy exists. Energy just always exists, and energy is always moving around. It moves like erratically. It's just everywhere, and there's no stopping it. Even in the perfect vacuum, it's still there. Now, even at absolute zero, energy still exists because of how quantum rules work. It is assumed 0 point energy is linked to dark energy as well, which is what pushes, like galaxies apart, basically, because the galaxies are always moving. We don't move, our galaxy does, and we're inside of the galaxy. We're like in the belly of it, So we assume that the Casimir effect is affecting like the actual entire universe too. Everything's being pushed apart because there is a constant moving of particles just pushing everything, and we just can't detect it. Well, we can detect it with the Casimir effect. We've detected it many times. And it's weird. It is weird, isn't it? Now everything, that's it. That's all the notes. Look, my drawer is empty. I didn't pick any topics. I went to quantum physics, and there were a lot of crazy sounding topics, right? A lot of crazy stuff. I chose to pick all the topics that have like some scientific backing to it, that were proven by scientific experiments. So anything I've said today, you can look it up, and there's probably tests proving it. With quantum mechanics, though, I will tell you, if you're interested in the subject, there's a lot more to it. There's a lot of more fascinating stuff to it that is more theoretical, unproven, and mostly theory stuff. But I think there's something to it, because I know most of the stuff I talked about seemed mundane. It's just mundane stuff, fascinating, interesting, weird, but nothing like groundbreaking. Just particles act weird, and especially small particles act weird. But there might be more to this quantum stuff. I don't know. I don't think I'm smart enough to understand quantum mechanics. I don't think I'm smart enough to understand quantum physics either. But at least from the scientifically proven stuff, it is very fascinating to think that, there's more going on in this world than we might think. And if you think the world's a matrix or whatever, or a hologram, or, the quantum stuff does kind of, I don't know. I feel like if you believe that we live in, like, the Matrix, the quantum mechanics make way more sense, honestly. Because, like, at that point, it's so bizarre, honestly. Well, I did try to skip most of the more fantastical stuff about this subject, because once I looked into quantum physics, I started to realize, like, oh shit, there's like some real stuff to this. Like, it's not just goofy conspiracy theory bullshit. There's like actual like scientists. There's actual like the Large Hadron Collider is a 17-mile underground facility that is specifically focusing on quantum physics. There's something there. It's fascinating. If you like science, Like, this is very fascinating to me. But I don't know. You know, maybe when I cover space, I've never covered space before on these topics. Maybe I'll find more fascinating stuff. Maybe we'll cover space and we'll think back to quantum mechanics and we'll start figuring stuff out, you know? But I had fun. I actually had a lot of fun, like, looking into this. Because it is super cool, actually. Like, I expected it to be, like, boomers talking about, like, alternate dimensions and bullshit like that. But no, there's some actual, like, tangible science to this that's really weird. And it makes me think, you know, like, holy shit. It's cool. But we're out of notes. And I don't know any more information about, you know. What is that? Oh, okay. We're going back to the back room. Where we belong. Let's see shit with the. Let me get my radio too. Well, I kind of bled through those notes real quick, but I was kind of hyper reading them too. I wouldn't say. Please let go of this. Please let go of this thing. Please. Please. Just let go of the camera. Please. Just let go of the camera. My guy won't let go of the camera. Oh, you guys are stuck with me now. There we go. Jeez. But I assume you probably might have actually been interested in quantum physics. Maybe I told you one or two things you didn't know about it, but I assume you seem like a smart guy. You probably knew a lot more than I did by default. You know, you probably looked into this 10 years ago and went, hey, yep, pretty cool. Let's see how many people we got. We'll see if we can rate anyone. Because unfortunately, I did my research, but there's just not a lot more about quantum physics I could talk about. Those are the main, like, things to keep into, mind. And they're not bad things, you know. But it's very fascinating. It's just nothing, like, crazy major, you know. It's nothing super, like, fantastical. We're not opening a dimension to, like, the fucking Stargate era, you know. It's just little things that don't quite add up. And really, there's nothing wrong with that. Yeah, we got 5 folks. That's enough to throw them some ways. Let me see if I can find someone a little more exciting. I'm sorry, I've been talking about fucking particle physics, you know. I can't help it. It's only so many ways you can make that interesting. You know, we'll just give it to Safarian. Make it easy on ourselves, you know. He's alright. He's playing American Truck Simulator, so be chill. Thank you, everyone, for showing up, though. For this schlock, this dumb topic I picked today. But I thought it would be real funny after doing a stream talking about Friday to just jump to quantum physics, although I know very little about it. I did my best. Oh, let me get you guys to the end screen. Oh. Hey, though, I had a lot of fun. I appreciate you guys sticking around, too. Next week, I promise you, maybe I'll pick a less demanding topic. Now, primarily, actually, I'll switch this back so I can talk to you guys face to face. You know, I just want to say something. I want to say something important to you guys. I want
unless they summon Vortiga.
Alright, you know what? At the end of the day, you guys take care of yourselves. Thank you. And keep your head on straight. I wish the best for y'all. Otherwise, enjoy the trucks. But yeah, take care of yourselves, guys. It's a tough world out there, you know. All you can do is do your best. I'll see you next time.